Alright, hello and welcome to Forces and Motion Lesson 2, where we will be going through a quick review of last lesson, the Suvat equations, a basic intro to forces, Newton's first law, Newton's second law, applying forces, and falling and parachuting. So, a quick review of last lesson. Well, what did we cover? First thing we covered was average speed. Oh, this is quite nice. Average speed. Speed equals distance over time. That's the first thing. Covered that formula. Then we talked about scalar versus vector, where scalar is a quantity which only has a magnitude, and a vector has a magnitude plus a direction. We also talked about acceleration. It's a bad bullet point. Acceleration being equaling, just get rid of this, equaling change in velocity over time taken. And we looked at distance time graphs and velocity time graphs. Distance time plus velocity, I'm just going to write VT graphs. And the key thing to remember there was two axes, was that firstly acceleration from a velocity time graph is the gradient. Acceleration is a gradient, and displacement is the area under the graph. So those are the key things we looked at last time. Now, on to today's lesson. So the first thing we're going to talk about is Suvat equations. Now this is kind of a continuation to where we left off last time. Well, as we saw, I defined acceleration. Let's just give it a nice title. Suvat equations. Little cloud around it. So, as I said, acceleration equals change in velocity over time. Right, now we're gonna use this equation, but in terms of symbols instead. Now, what is change in velocity? Well, it's simply the final velocity minus the initial velocity over, and then time is just t. So, as I just showed you, velocity v equals final velocity. This is a common terminology that's going to be used throughout your GCSEs. So v is final velocity, and u is initial velocity, and t over here is just t equals time taken. So you just got to become familiar with these symbols. Now that takes us on to the Suvat equations. Now, what are Suvat equations? Well, Suvat equations are equations of motion when acceleration is constant, to help us find out different physical quantities that we want to measure. So we have S, U, V, A, T. Hopefully this will make it clear. So S is displacement, as discussed in my last video. It's a bit mind-boggling that because you can get it confused with speed, so you got to be careful. U is initial velocity, as just discussed. V is final velocity, as just discussed. And A is acceleration, and T is time. Now, I'm going to write down the equations here, and I'll tell you how we can use them. So, firstly, V equals U plus AT. Secondly, let's just do, what should we do? S equals UT plus, actually no, that's a little bit harder. We'll go in order of what's easier and what's a little bit harder. S equals half T U plus V. 3 S equals UT half plus half AT squared. 4 S equals VT minus half AT squared. So I'm not sure if you need the fourth one, because that's something that comes up in A level, but not so much in GCSE, but it's useful to remember anyway. S equals VT minus half AT squared, and 5 V squared equals U squared plus 2AS. Now, what do all these different equations mean? Well, there are, as we discussed here, there are five different quantities here that we want to measure. If I just write this down, 1, 2, 3, 4, 5, and there are 5 different equations here. Now, what that means is that each of these equations omits one of the physical quantities. So this equation here does not include speed. So I'm just going to write equations. It does not include, oh no, does not include, so the equation 1 does not include, displacement. Oh, I got that mixed up. Sorry, so equation 1 does not include displacement, equation 2 does not include acceleration, equation 3 does not include final velocity, equation 4 does not include initial velocity, and equation 5 does not include the time. So what that means is that if you're given a set of parameters, let's say you're given, it means that you only need 3 of them to find out something about a fourth. You only need 3 of these parameters to find out about, you only need 3 of these quantities to find out about a fourth one. So let's say there's a question over here, and then let's say 1. Oh, that's going to be a bit confusing. Let's say example 1. You are given the displacement S equals 100 meters, acceleration equals 5 meters per second squared, and let's say U equals 0. So now, using this equation, even though you do not have the time it took for this whole movement, you have these 3 quantities, and now you can find the final velocity of the you can find the final velocity, and you can also find the time taken. So let's just find the final velocity. V squared equals U squared plus 2AS. You do some rearranging. V equals U squared plus 2AS. You can plug in the numbers. Equals 0 plus 2 times 100 times 5. So 2 times 100 times 5. 2 times 100 times 5 equals 1 square root of 1000, and you can easily just work that out, just get your calculator out, and that gives you a speed of 31.6 meters per second. So that's your final velocity using those Suvat equations. Now, with the same three physical quantities that we were given, we can find time. So let's just look at the equations up above. We are not given, let's pretend that we haven't figured out the final velocity yet. We're not given v, so which equation omits v? It's this equation, equation 3 omits v. So we're going to use equation 3 to find the time of the whole process. So equation 3 is s equals ut plus, s equals ut plus half a, this is getting a bit rough, sorry, s equals ut plus half a t squared equals, and then we want to rearrange for t. We can take ut out because u equals 0, therefore u times t equals 0. Therefore s equals half a t squared, 2s equals a t squared, t squared equals 2s over a, t equals root 2s over a. Now we just plug in the numbers. 2s, what was s? S was 200, so root 200, my pen broke, give me a sec. T equals root 200 over a, over the acceleration, which is 5. So 5, and we just plug that in, 200 over 5, and we get a speed of we get a time of 6.32 seconds. 3 significant figures. Hopefully that has given you a brief introduction to Suvat. Just to sum it all up again, we get 5 equations, and we use the one without the parameter, without the physical quantity we are given, we are given 5 equations, and we use the one without the physical quantity we are not given to find out a physical quantity we want to know. So if we don't have s, but we have v, u, and a, and we want to find t, we use the first equation. So you need to practice lots of questions of Suvat equations and just get used to knowing which ones to use. It really helps to have clear working, because then you can see which, like if you just set it out like I've done here, it's quite easy to see. So the quantities you're given, and you know the ones you need to find out, and you know the ones you don't have, and therefore you know the equation you need to use. So yeah, those are Suvat equations. If you are still confused, you can email me and we can work through that. Okay, now we're going to talk about forces. Intro to forces. Okay, so I think the course wants you to know 3 basic things. Well, firstly, a force can cause an object to change shape, speed, or direction. So when we talk about changing shape, you can think about a rubber band, and when we talk about changing speed, I mean, we'll talk about Newton's second law, and we'll talk about acceleration. And when you talk about change, just these are the basic things. So if I give an example for each, stretching a rubber band changes its shape. Stretching rubber band, changing an object's speed, applying a braking force. That's not clear. I don't even know if I spelled that right. Applying a braking force force reduces velocity of a car. Velocity of car, and if you are traveling in, so you're traveling in this direction, and then someone pushes you in this direction, you're gonna change the direction because of the effect of the force that he pushes you with. So those are the consequences. Those are the three things that forces can do. And as we discussed earlier, force is a vector. Force is a vector, which means that we can add and subtract forces to get a resultant force. Now, I'm going to try draw a car. There we get this. Okay, so this is a car. I don't know what kind of car. It's got the wheels over here. Got a window over there. So, the car has a thrust of 100 newtons in this direction. And the unit for force is a newton. Don't worry about it too much. We're going to go on to that soon. Just stick with it. So the thrust of the car is 100 newtons. I'm just going to label that thrust. And the frictional force of the car is, well, it's not going to be, let's say that it is 20 newtons. 20 newtons friction. So because force is a vector, it can be added and subtracted depending on the direction. So 100 minus 20 equals 80 newtons, which gives us a resultant force of 80 newtons in the direction to the left. So the car has a resultant force of 80 newtons. So that's just an example of adding and subtracting forces, and you can do that because force is a vector. Now, the third thing that they want you to know is, they only want you to know those two things. Okay, so they want you to know that forces can cause objects to change shape, speed, or direction, and force is a vector quantity, and therefore you can add and subtract forces. Now, Newton's first law is a famous one. They're all famous. Newton's first law. I think it's best for me to write out a definition so that you guys can remember it. Definition. Okay, so if there is no resultant force on an object, the object either stays at zero, the object either stays at rest or continues in its current just getting used to writing with these pens, or continues in its current state of motion. Now, I think you guys should read that. Just suck that up for a second. Pause if you have to. I'm going to give you two examples to help you think about this. So, first, the same car. Well, I'll try to draw the same car. Don't know what that is. So the same car. Let's say it has a thrust of 50 newtons and a frictional force of 50 newtons. Friction because of the wheels along the ground. So friction is a force that opposes the direction of movement. So let's say that it has a... Yeah, actually, let's talk about this first. So the car has a velocity of 5 meters per second in this direction, the direction of the arrow to the left, and it has a thrust of 50 newtons and a frictional force of 50 newtons. Now, what does that mean? Does that mean the car will stop? Pause and see if you can think about it, but basically it does not. What it means is that it does not stop, continues at 5 meters per second. Now, that's because of this rule, this law, that there is no resultant force, because 50 minus 50 is 0. The object either stays at rest or continues in its current state of motion. Now, the object cannot stay in rest because it already has a state of motion, and that motion is a velocity of 5 meters per second to the left. So the car simply continues at 5 meters per second. In other words, it stays in its current state of motion. Now we can think about a simpler example. Let's draw. So this is me standing on the ground, and I have a weight of, let's say I have a weight of whatever. Let's say I have a weight of W equals mg. Let's have a weight of 600 newtons. That's right, 600 newtons, and there's a contact force from the ground of 600 newtons up on me. So we're going to talk about this soon, but this force is weight, and this is the contact force from the ground. You guys can feel that right now if you want. I mean, you can stand up. You have a force towards the earth because of gravity called weight. We're going to talk about that in more detail soon, but yeah, that's the force forcing you towards the ground, and the ground exerts an equal and opposite force up onto you. We're going to discuss that in next lesson, actually, Newton's third law. But anyway, don't worry about that now. Just look. There's weight in this contact force. The lesson to be learnt here is that there is no resultant force, and I have zero velocity. Therefore, I will stay at rest. So those are the two applications of Newton's first law. So object in motion stays in its current motion, does not accelerate, does not decelerate, most importantly, and object at rest stays at rest. Alright, okay, now let's talk about Newton's second law, which is more fun in my opinion. I need to rub this off the board, sorry, give me a sec. Right. Newton's second law, an all-time classic. Well, it's mostly remembered by this formula. Force equals, let's just write that out fully. Force equals mass times acceleration, and the units are newtons, kilograms, and, as we discussed earlier, meters per second squared. So that's the unit for force, as you could probably get together. You don't really have to know this for GCSE, but Newton is equal to kilogram meters per second to the -2. Anyway, you don't really need to know that, but you can just figure that out from looking at the equation. Anyway, force is equal to mass times acceleration. Now, in your exam, if it asks for the definition, or if it asks for what Newton's second law of motion is, I would prefer if you give this definition, because it's kind of guaranteed to get you the marks. Acceleration is directly acceleration is directly proportional to the resultant acceleration is directly proportional to the resultant force and in the same direction as the resultant force, and inversely, let's make that clear. Sorry, this writing is tough for me. And inversely proportional to the mass. So let that sink in for a second. Acceleration is directly proportional to the resultant force and in the same direction as it, and inversely proportional to the mass. Another way of thinking about this is just looking at the equation and rearranging it. So force equals mass times acceleration. Therefore, acceleration equals force over mass. Acceleration is proportional to the force, and acceleration is inversely proportional to the mass. So those are two ways. That's a way of thinking about the definition I just gave you. This is the basic equation: force equals mass times acceleration. In symbol form, it's just F equals ma. That's what's going to get you a lot of marks in your GCSE. Just rearranging that equation and understanding it, and this definition will definitely come in handy as well. Yeah, so hopefully that explains that to you. Now let's talk about an example. We talked about our famous little car over here. Oh, whatever. My car drawing is going downhill now. It's a new car. It's the newest, latest edition, newest car. Let's say it has a thrust of 100 newtons and a friction of, let's try and make that more even, and a friction of 90 newtons. Alright, so let's also say that it has a mass equals no need to draw this higher actually. Let's say it has a mass of mass equals, how heavy is a car usually? Let's say a mass of 700 kilograms. I can predict that this car will be moving slowly. Anyway, let's find the acceleration of the car using Newton's second law. So if you can work it out if you can pause and work it out, and then look at how I do the solution anyway, just to give you a sense of how to set it up so it's neat and you get all the marks even if you don't get the final answer correct. So you do N2, so that means Newton's second law. You resolve in this direction to the left. So you define that as the positive direction. You do F equals ma. You just get the formula right out of the banks. Right out of the whatever. You get the formula right out there. You do 100 minus 90, that's the force. What you can do first actually is rearrange this equation. I do A equals F over M. Get A equals 100 minus 90 over 700. Now you can plug that into your calculator. So basically just 10 over 700, and you get an acceleration of 0.0143 meters per second to the minus 2 to 3 significant figures. Now that's a small acceleration, but that's the answer we got for this car. Hopefully that explains to you Newton's second law and just a basic problem. If you have any questions, again, email me and we can talk through them. These are just the basic building blocks, and you need to work around these and do some trickier questions. And yeah, let's talk about applying forces now. Let's talk about it. Applying forces, right. Applying forces. We're going to talk about specific forces now. So let's talk about weight. Now, what is weight? Weight is a force. Weight is a force. Is a force that acts on an object. That that acts on an object that acts on an object with mass towards the earth because of gravity. Now, one thing you cannot do, because it will annoy all your physics teachers, including me. Gravity is not the force. Gravity causes weight. Gravity causes weight for an object with mass. Causes weight for an object. It's actually, let's rub that out. That's not technically appropriate by me. An object with mass. So basically, any object with mass, gravity acts on an object with mass. Acts on an object with mass, causing weight, which is a force. So, to reiterate, gravity is not the force, weight is the force. Now, how do we calculate weight? Well, if we look at the formula that we were just using, let's go underneath. I think that looks slightly better. So let's use the formula that we just had. Force equals mass times acceleration. The force is now, as we just discussed, the force is weight. Well, we just say an object with mass, gravity acts on an object with mass, which causes weight, so mass can stay there. Mass is there. And what is acceleration? Well, when we're on the Earth, the acceleration is a value we call g. So g is the gravitational field strength. And it is defined by the acceleration, of free fall. So when you're falling, what's your acceleration towards the Earth? And that is given as a value of 10 meters per second squared. In this physics GCSE syllabus. When you do A levels, like 9.81. But yeah, you can just remember it as 10 for now. Weight, as we said, let's just get these units in here. Weight, as we said, newtons. It's just a force. Mass is kilograms. Why stop working? Mass is kilograms, and g is meters per second squared. Alright, that's how you can remember it for now, or you can just rearrange it. You can get g equals w over m equals, and then you can just use the unit to get you can use newtons over kilograms to show that g is equal to newtons per kilogram. So that's the same as newtons per kilogram. Alright, so that's weight. Weight equals mass times gravitational field strength. Now, one thing to remember is that gravitational field strength, I should have been more specific. Gravitational field strength on Earth is 10 meters per second squared, but it changes on other planets or when you're at different parts of the atmosphere, to be exact. But for example, the gravitational field strength of Mars is so G values. Mars equals 4 newtons per kilogram, and Jupiter, actually let's just put the Earth in there for the sake of it. Earth equals 10 newtons per kilogram, and Jupiter is roughly, oh my gosh, what's happened there? Jupiter is roughly 26 newtons per kilogram. Now, you could probably tell that the gravitational field strength increases the more massive a planet becomes. So Jupiter is a lot bigger than Earth, significantly larger than Earth, therefore its gravitational field strength is stronger. That's not something you have to worry about now, it's just something you have to recognize and apply to your problems. And yeah, in exams, you'll either be given the quantities to work out what G is, or they'll tell you what G is, so you don't really have to worry about that. Let's actually do a quick example. Let's say, example, right, whoa, example, we are on Jupiter. G on Jupiter is given in the exam as 26.5 newtons. Let's make that neater, shall we? The G value on Jupiter is given at 26.5. Why is it not working all of a sudden? 0.5 newtons per kilogram, and I have a mass of 60, let's say 70 kilograms. Now, using these values, can you calculate what my weight on Jupiter would be? You can pause and do that. I'm just going to work through it now. Simple, weight equals mass times gravitational field strength equals 70 times 26.5. I am not smart enough to do that in my head, so let me just get my calculator out. Equals 1855 newtons. So that's my weight. So I think one thing you could have recognized by now is that if I weigh 70 kilograms on Mars, that means I'm gonna weigh if my mass is 70 kilograms on Mars, then my mass on Earth would be 70 kilograms, and my mass on Jupiter would also be 70 kilograms. Your mass does not change depending where you are. The gravitational field strength does, and hence the weight changes depending on the change of gravitational field strength. Alright, so that is applying forces. Hopefully you understood that. If you don't, as I said, you can email me. I think I say that many times a lesson. Let's now talk about falling and parachuting. This is actually, I really enjoy this little bit of the course. Falling and parachuting. Now, I'm just going to tell you in advance what we're going to do. We're going to come up with a speed time graph of what happens when you jump from one of those planes and you fall and you release your parachute. What happens with your speed and what happens with your time? Well, let's take a look at it, and we're going to look at it in terms of forces. First, let's split the journey up into different parts. So, part A of the journey. You are stupid enough to go skydiving. Well, I don't actually mean that. I have no idea. I've never been. So you go skydiving. You jump out of the plane. Now, on the moment you come out of the plane, the moment you jump out of the plane, this is you. You are here. You're smiling. You're really excited. You've broken your arms for some reason. So that's you. You're skydiving. On the moment you jump out of the plane, there is no air resistance acting on you because you've just jumped out of the plane. There hasn't been enough time for you to, there hasn't been enough time for you to start moving downwards and air molecules, preventing your fall. So there's no air resistance on the moment you jump out of the plane. So you only have weight. Now, what that means is that your resultant force is really large at part A. So at the beginning of the journey, resultant force is really high. Well, it's at its highest anyway. So resultant force is high. What does that mean? F equals ma. F equals ma. A equals F over m. Now your resultant force is high, but your mass is the same. What does that mean? You have a large acceleration. You have a large acceleration. There we go. Now, that's part A of the journey. Let's talk about... How can I make this smaller? Let's make this smaller. Let's talk about part B. Part B. Alright. So now you've jumped out of the plane and you are moving downwards. You are going downwards and air resistance starts to work its magic. Sorry, I've really got some technical difficulties today. Those will improve. But yes, air resistance is starting to work its magic and you get even more happy. Slightly so. So, air resistance starting to work its magic. You've broken both your arms for some reason. You still have the same weight and now air resistance is increasing. It hasn't quite matched your weight yet, but it's increasing. So air resistance, so let's just write here the air resistance increasing, resultant force decreasing, and therefore acceleration is decreasing. Right, now we look at part C of the journey. Now part C is simply when air resistance becomes equal to your weight. Now what happens there? Here you are, happy as ever. Part C, air resistance, I'm just going to call it AR, is equal to your weight. So weight is equal to AR. No resultant force, hence no acceleration. Now this point, when this happens, we just write hence no acceleration, it is called your terminal velocity. So the velocity at which weight equals air resistance and there's no acceleration is your terminal velocity. We'll look at that again in the graph. But just note that down mentally for now. Terminal velocity achieved. Now, let's say you're going down and bang, you pull your parachute out. And let's just zoom up a bit so we don't lose track of the others. Part C, right. Part D. So, Part D, now you're a bit sad. Let's say your eyes have changed, but you're less happy going this way. Your weight is still the same, but you're pulling your parachute now, so you're less happy because your skydiving adventure is coming to an end. Your parachute goes up, so therefore your air resistance increases, so AR increases. Your air resistance becomes larger than your weight, which means you have an acceleration upwards. Acceleration upwards, or more conveniently, if we define going down as positive, there is a deceleration. Now, there's a deceleration, and a common misconception I think everyone in my class had in school is that when you are parachuting downwards and when you are skydiving downwards and you pull, so let's say this is you're parachuting downwards and you're parachuting downwards and you pull your parachute, then for that moment you just go really high up in the air. No, that's not actually what happens. So basically what happens is you're still moving downwards, you still have a velocity downwards, it just decreases because there's an acceleration in this direction. So, just to reiterate, when you pull your parachute when you're skydiving, your velocity does not change direction. Your velocity stays in the same direction, so your velocity stays positive. You're still going down, but much slower after the deceleration of the parachute. So you still have so as we said, part D, you still have a velocity downwards. there's deceleration, still a velocity downwards, a velocity towards the ground, but you are decelerating. Now, oops, what have I done there? This is so slow, give me a sec, sorry. Oh, is it crashed? No, it's fine. Right, now, let's talk about part E. Part E is simply when you reach your second terminal velocity. Now your air resistance, you're not happy now. You got a moustache as well. So your air resistance increases, your air resistance decreases because you're not moving as fast, and air resistance is proportional to velocity, because the faster you go, the more air molecules are hitting you and preventing you from basically traveling downwards. Air resistance decreases. So, oh gosh, it's crashing. So, this is weight, air resistance decreases till air resistance equals weight. You reach your second terminal velocity, your second terminal velocity at a lower speed, so lower magnitude, at a lower speed, and then part F, you hit the ground. So this is the ground, this is you standing on the ground. There you go, you're happy. You're scared you're going to get hurt, but you lived. Your body may have disappeared and your legs may have got longer, but you have hit the ground. Now, what we're going to do is we're going to look at all of these parts and we're going to draw a graph. So, part A, B, C, D, we've got them all here. Load will, yeah, there we go. Hopefully you can see all of that. So we got falling and parachuting. So, let's get the speed time graph out. This is the time in seconds, and speed. No, come on, let's make that neater. And speed in meters per second. Right, so let's get this going. So as we said, as you jump from the parachute, you initially have zero velocity, but your acceleration is high, so your speed increases and increases. So you're supposed to start at zero, but my stylus is a bit funny. Anyway, so you're starting at zero, but then air resistance slowly starts to catch up with you. It catches up with you, then bang. Oh no, what's going on? You know what, I'm going to be less expansive with the graph here, so I have enough space. Classic mistake. Right, so as I said earlier, as I just said, you have a large acceleration, hence the gradient of the speed time graph. You have a large acceleration, air resistance starts to kick in until slowly you reach terminal velocity, where your speed stays constant. Oops, come on. Where your speed stays constant, then bang, the parachute opens quickly and you reach the terminal velocity there and you hit the ground. Okay, so if you can draw that out and then try and draw it out and then label each part of the graph with the parts of the journey that I just discussed before. So part A, B, C, D, E, and F. You can do that now and pause. I'm just gonna kind of label them here. So this is kind of part A here, where your acceleration is greatest because there's no air resistance, and then this whole part here is part B because your air resistance increases as you go downwards. Your velocity is increasing downwards as your acceleration so because your acceleration is at greatest, your velocity is increasing, and as your velocity increases, more air molecules hit you on your way downwards, preventing your motion. Thus there's air resistance increases with your velocity, and as air resistance increases, it becomes more and more equal to your weight. So there's a deceleration as the resultant force decreases. Now we go to, well not exactly actually. This part of the graph should be flat. It should just be like 180. It should just be, so part C, forget about this overlap, don't worry, that's just me and my technical issues. That's part C of the graph when weight equals air resistance. There's no resultant force, hence no acceleration, and this is your term of velocity. So you're going to travel at this velocity where weight equals air resistance. This is your term of velocity number 1. I'm just going to label it TV1, terminal velocity number 1. And then you open your parachute and bang, there's a deceleration. There's a large deceleration, but you still have a velocity towards the ground. So your speed, you still have a speed, but it decreases quite rapidly because of the parachute, and it keeps decreasing until air resistance becomes equal to your weight, and your air resistance decreases because your velocity and your speed is decreasing. So your air resistance decreases and it becomes equal to weight, and that is your term of velocity over here, which you stay at. So TV2, TV2, and then you hit the ground. So just to reiterate here, let's think about this in terms of forces. At A, let's zoom in. At A, weight is greater than air resistance. Just try and think about this in terms of forces. At B, air resistance is increasing, but weight is far greater. So at A, weight is far greater than air resistance. Far greater than air resistance. At B, weight is still greater than air resistance, but that difference is decreasing. At C, weight equals air resistance. At D, air resistance is greater than weight, hence the deceleration. And at E, when there's term velocity, weight equals air resistance, and then you hit the ground. And there is no air resistance, but anyway, you're at the ground, so don't worry about that. Right, so that's the lesson for today, Forces in Motion, lesson 2. I hope you enjoyed it. If you have any questions or feedback, please feel free to email me. I'll keep my email in the description below. And yeah, hope you enjoyed and understood.